So last video we laid the foundations for inference for two proportions, and this one we're going to apply those foundations to an example. So on page 71 in your notes, we've got this example of a very large study from the National Institutes of Health, or NIH, and we see that we have data from 2,253 men and 2,629 women. And out of these young men and young women, the age 19 to 25, our research question, we want to see if there's good evidence that different proportions of young men and women are still living with their parents in that 19 to 25 age range. We're going to practice this in two different ways. One using a hypothesis test and two using a confidence interval. And we're going to notice how those two different approaches agree with one another. So anytime we're comparing two different groups, I would strongly suggest first kind of defining what is group one, what is group two, and any information they give you on those. So I'm going to say let group one be men, just because that's the first bit of information they give us up here. And they tell us our N1, or our sample size for group one, is 2,253. Then group two, I'm going to define to be women. And just a note, you could define these, group one is women, group two is men. It makes absolutely no difference. Choose how you're going to define it and stick with it through the entire problem. So our N2 are the sample size for group two, the women. They tell us we have this 2,629 women. Then they also tell us how many in each group are considered quote-unquote successes, are still living with parents. So my P1 hat, based on the data, not the entire population, for the first group of men, I see that I've got 986 successes. Out of the sample size for the first group, that 2,253. And remember, just for convenience, we're all going to be rounding to 4 decimal places, so we get kind of the same thing. So here I've got 0.4376 if you plug that in and round it to 4 decimals. All right, then our P2 hat are based on the data for group 2, or women, the proportion of successes. We've got 923 out of our total sample size of 2,629 for the women, and that should give you 0.3511. All right, so we've defined what's group one, what's group two. We've jotted down any information, and we've identified their research question. They basically want to see, are men and women living with their parents at this young age range in different proportions? They don't really have a thought on if one group's more or less than another. Is it just different? So let's first answer this with a hypothesis test. I know it says confidence interval here. Let's switch it up, do hypothesis test first. So our hypothesis test, remember we've got 5 steps we need to work through here. Our first step is stating our hypotheses. If you need to go back and review, check out the previous video for laying the foundations or framework for a 2-proportion hypothesis test. So first step, state our hypotheses. We've got HO and HA. Our initial assumption is always going to be that the two groups have the same proportion. There's no difference in the proportions of men and women living with their parents. Remember, we had an alternative way we could write this. Just choose one. You don't have to write both of these down. I'm going to write both just for practice. Saying they're the same is the same thing as saying their difference is 0. There is no difference in the two groups. Then HA, comparing these two proportions, I don't think they're the same anymore, and my research question here is just to test if the proportions are different. They don't have a theory on who's more or less. So that means my symbol in HA is going to be not equal to. Our other method for writing this is going to be P1 minus P2 is not 0. There is a difference. It's not zero difference. We don't know what it is, but there's a difference somewhere. So again, initial assumption, assume they're the same. Research question, can we show they're different? Okay, next bit we need to calculate our test statistic. So step 2, our test statistic, remember this is just our fancy z-score. And our numerator had our data, so the difference in the proportions for our data set. Again, if you need a review of the formulas, check earlier in your notes on the previous page of the last video. So our P1 hat, or the proportion for the first group, was 0.4376. I'm going to see how different that is from my P2 hat, or proportion, from the second group based on the data. Okay, so here's my difference in the two groups from my evidence, or the data I've collected, minus the null hypothesis. I'm always measuring how far is my data from my initial assumption. We set up here the difference of the two groups is 0. That's our initial assumption. So I'm going to put minus 0. Again, if you don't want to write down this minus 0, you don't have to, but I really like emphasizing that idea of checking out how far the difference is in the data versus our assumption under the null hypothesis of no difference. Then we need to standardize this guy. So our null said that the two groups were the same. P1 and P2 are the same, so we need this common same proportion to use in our standard error. So let me find it up here. We called this just our P hat. We didn't have a subscript because we're assuming it's not two groups, but one common group. So just combine all the data together. We've got 986 successes, or men living at home, and 923 women living at home here. So all the successes, if it's from one common group, over our total sample size when we combine this as if it's one common group. Now, when you calculate this, your answer should always be between your P1 hat and your P2 hat. It's sort of like an average, and it's weighted a little bit by sample size. So your answer should be between these guys. If you work it out and round to 4 decimals, you get 0.3910, which sure is kind of in between 43 and 35%. All right, so this P hat is for hypothesis test only. Don't use this in the confidence interval. This is because the null is true, we're assuming the proportions are the same, and we got to find that same value for our test statistic. Don't use it in a confidence interval. All right, so that goes down here. This is our P hat, 0.391 times 1 minus 0.391. And we had 1 over each of our sample sizes left over. So when we pulled out that common proportion, so 1 over our 2253 plus 1 over our 2629. Again, all of that's under 1 square root. I'm going to work this out in 2 steps because there's a lot of room for error in the calculator. If you work out the numerator, we get 0.0865. So this is telling me that based on the data, I observed that the two groups are somewhere between 8 and 9% different. The proportions are different by between 8 and 9%. Then our standard error, we would expect this to vary from sample to sample by 0.0140 when you work out the denominator or the square root term. Putting those together, you get a z-score or a test statistic of 6.1744. And this is huge. You guys know about z-scores. Most of the data are between plus or minus 3, z-score of plus or minus 3. This is 6. This is way out there. So this is telling me a difference of 8%-ish in the data is very, very, very different from the assumption of no difference in the populations. Okay, so let's put that in terms of a probability now. What are the chances of my data being that far away from an assumption of no difference? So that's step 3, our p-value. So go ahead and draw a picture to help avoid making careless mistakes. And try and draw it sort of to scale. So here we've got our plus or minus 3, where most of our data is zeros in the middle. Our test statistic is somewhere way out here in no man's land, this 6.1744. Now if you remember, our HA is not equal to. So that means I want to find the probability of being that far off up here in the positive direction. So I'll circle this area, but then also that far off in the negative direction, because I'm not sure which side. So this area. So our procedure was, let's find one of these and just double it. Again, you know enough about z-scores in the normal curve that you know there's not too much out here. So when we work this out, we expect to get a number that's really, really, really tiny. So in this case, our p-value, or the probability of getting our data that far away from the assumption of no difference, is going to be, I'm going to find this upper tail. You could find the lower tail if you wanted. I'm going to say normal CDF to find that area. My lower in this case is my statistic of 6.1744 out to infinity. That gives me just this bit. I need to double it to get the bottom part, again because HA was not equal to, so it's two-sided. And if you work that out, you get a really tiny number as we expect, something like 6.7 times 10 to the negative 10th. So don't forget that times 10 to the negative 10th. Remember, your calculator might say E negative 10 for engineering notation. That's all it means, times 10 to the negative 10th, or move your decimal left 10 times. So that's a 0.9 zeros and a 6, 7. Really, really small chance. Okay, let's interpret that number so we're sure we know what it means. So step 4, interpret the p-value. When we interpret it, we said make sure it's always in terms of the null hypothesis. Let me just make a note here, interpret p, and reminder, always in terms of HO, because that's what we plugged in up here. We plugged in the null hypothesis of no difference, and we assumed no difference to calculate this common proportion. All right, so this is telling me if the null is true, and in our setting, that means the proportion of men and women who live at home, it's the same, no difference. So we'll say if there is no difference in the proportions of men and women living at home, so again, that statement is our null hypothesis, putting that in words. So if the null is true, no difference in proportions of men and women living at home, we would see data like ours. That's our z-score we calculated. Or more extreme, that's the part we shaded on either tail here, according to HA. And then turn your p-value to a percent. So remember to multiply this by 100. If you do that, you get 6.7 times 10 to the negative 8th percent of the time. Okay, so that's really tiny. If there's no difference, I'm basically never going to see the data is what this is saying. So that's telling me there probably is a difference. So that's what we're going to write down in our last step, our conclusion. And remember, our conclusion always goes back full circle, should be in terms of our research question, HA. We're going to say how much evidence we have for that. So in this particular case, I'm going to say there is, and I'm going to just kind of leave a blank here for a minute, and we'll go back and think about it, but we're saying how much evidence we have for HA, so we have some kind of evidence for HA. Let's put HA in context, so check up here. HA was saying the proportions are different proportions of men and women live at home. So there is some kind of evidence, we'll figure that out in a moment, that the proportions of men and women living at home are different. So again, don't get caught up in all the wording. All that is doing is just putting HA in plain English for somebody. So let's go back to what kind of evidence. If you need to, you can flip back in your notes to our little guideline page on bottom of page 68. Or in the last video, we summed this up on our summary page. So our p-value is really tall or small, much less than 1% of the time. So we have very strong evidence. If the null is true, we'll basically never see the data. So we have really strong evidence for HA. So there's very strong evidence. It's what we'll fill in our blank with. Again, because our p-value is really small, less than 1%, we have very strong evidence for our research question. Okay. Let me ask you a question, and then we'll have a little bit of a break here and let you try. So let's check out the confidence interval and see what we would get here. But before we check it out, let me ask this question. I'll say, based on the hypothesis test, okay. So we mentioned confidence intervals, hypothesis test, those results should agree. So based on the hypothesis test, would a confidence interval for P1 minus P2, same setting about men and women living at home, contain 0? Okay. I'd like you guys to think about that, come up with an answer without calculating the interval, just based on the work we did. Then go ahead and construct the interval to confirm. Once you've tried all this, check out the next video to see if your thoughts were going in the right direction here.